So after we studied naming of alkanes, cycloalkanes, the next two topics, a very small one, are to discuss the physical and chemical properties of alkanes and cycloalkanes, basically. Okay, the reason this chapter, this part is small, especially chemical properties. Normally we're talking about chemistry, right? We should spend a lot of time on chemistry, on chemical properties. But alkanes, in this level of organic chemistry, is a group of molecules has very limited reactions. Okay, so we don't study the reaction a lot for alkanes, okay, especially for this fundamental organic class. But in the next few chapters, our focus will be based on reactions. So this chapter, property study, is going to be smaller. But that's how every chapter will be organized. Okay, you will notice that after chapter 2 as well. We're talking about what? Structure, naming, physical property, and chemistry. Basically, that's how every chapter will be aligned for the first 6 chapters. Okay, physical properties, meaning those properties without chemistry, without chemical reactions. Okay, without changing the identity of those substances. Okay, mostly when we talk about physical properties, we'll talk about 3 things, which we're gonna show right now. Okay, first, about physical property for alkanes is their solubility. Okay, is their solubility. Alkanes are nonpolar molecules. Okay, they're nonpolar molecules, meaning on their molecules surface there aren't much charges unevenly distributed. Okay, they're nonpolar. And when we talk about solubility, the most important solvent on our planet Earth is what? Water, right? We're planet water. So when we talk about solubility, we first want to ask, does this thing dissolve in water or not? Water is a polar solvent, and they don't like each other. So, in summary, hydrocarbons, including alkanes, don't dissolve in water. Okay, don't dissolve in water. And we call that property, using a word, hydrophobic. Okay, hydrophobic. When something doesn't dissolve in water, and you still add to water, what would you see? 2 layers, separate. Okay, separate. The same as you pour oil in water, what you see? 2 layers. And the principle is the same. Oil is nonpolar. Water is polar. They don't like each other, so they don't dissolve with each other. Hexane, again, hexane is colorless. They added some dye here to show you the color. Okay, I think it's the iodine here, show you the color, so you can see the 2 layers. Okay, we will do that in our lab as well in week 3. You will add alkanes in water to see it will float. Okay, why does it float? Because hydrocarbons, their density is smaller than water. That's why they always float on what? On the surface. The top layer will be alkanes if you put them together. This is a lot of hydrocarbons, so you see 2 layers. If you only add a few drops, you will see some beads floating on surface. So that's the first important physical property of hydrocarbons, including what? Alkanes. Okay, I keep mentioning hydrocarbons because hydrocarbons, they all share very similar physical properties. They're hydrophobic, they're less dense than water. Why they're hydrophobic? Because they're nonpolar. Water is polar. Okay, water is polar. Next. Because the molecules are nonpolar. Okay, molecules are nonpolar. Molecules themselves don't interact as strong because there is no charges like attracting each other for the molecules. So it's very easy, the molecules of hydrocarbons or alkanes themselves to separate from each other. This reflects to the property that hydrocarbons, including alkanes, generally have very low boiling point. Okay, very low boiling point. Low boiling point means what? They boil at very low temperatures. Why? Because they separate, right? It's very easy. You don't need much heat to separate them apart. What's boil? Changing from liquid to what? To gas. Okay, to gas.
So weak bonds?
Yes, very weak bonding between molecules. Between molecules, we're not talking about within a molecule. Boiling is physical properties. The molecules themselves are still intact. You're separating molecules apart. Okay, hydrocarbons, their boiling point and melting point is very low. Okay, very low. Even they're all low, but we do have a trend for continuous chain alkanes. What is continuous chain? Means what? From ranging from 1 carbon to 2 to 3 to 4 to 5 to 6 to carbon. Continuous chain carbons. And the trend is here. What is the trend? When you increase the number of carbons, so basically the molecule is what? Bigger and bigger and bigger. The boiling point what? Increases. Okay, that's a very useful trend. Okay, very useful. I'll show you how useful that is. And you can see that for this boiling point chart, this line shows you room temperature. This temperature is room temperature, around 25 degrees Celsius right now. You can see these 4 hydrocarbons, methane, ethane, propane, butane, these 4 hydrocarbons, their boiling point is below room temperature. Means what? Means the boil already at room temperature. Means what? What does it mean something already boils at room temperature, like now?
It's a gas.
They're gas. These 4 alkanes, they're gas. Naturally, they're gas. Somebody say, my propane in the tank is liquid. I can shake and hear it. Because they're what? Highly pressurized. Your tank has very high pressure. You open that valve of the tank, propane tank, you see what? Gas come out. Because they're gas. Okay, they're gas. And starting from pentane, you get liquid, but still the boiling point is low. If you smell pentane, it's very strong because they're super volatile. Okay, it's very useful trend. Okay, this chart shows you as well. See that? Okay, as well. It's called a homogeneous series. Basically, you're increasing 1 carbon, one after another. You can see the boiling and melting point what? Increases. Okay, increases. Quick question. Which of the following alkanes has the highest boiling point? D-octane, right? Because see what? Highest number of carbon. See that? I won't ask you. I told you in your exercise Tyson quest, you don't even see, you need to write a few more words except naming. Other than that, you're only answering with either choice or a join. That's your language for chemistry. Or we're not doing English to an essay or something. Okay, never. Okay? Now, those are chain ones. Okay, those are chain ones. When you have a few hydrocarbons with the same number of carbons, okay, for example, 5 carbons. Okay, 5 carbons. Here, this chart shows you the boiling point are slightly different between branched versus cyclo versus unbranched. Okay, unbranched. Usually cycloalkane, okay, cycloalkane have higher melting point than the non-cyclo version. And branched ones have lower melting point and boiling point than the unbranched ones. Okay, unbranched ones. Okay, see these are 3 lines. See that? 3 lines. Okay, the green one is what? Cyclo. The purple line is linear, unbranched. The blue ones are some branched ones. So these are some difference. Especially branched ones will have a lower boiling point than the unbranched ones. That's related to molecule packing. Okay, just very briefly. Okay, you don't have to know deep on this. When molecule is linear, not branched, They're like what? They're like a stick. So they can very nicely pack with each other. So the packing is tighter. Tighter means what? You take more heat to separate them. When molecules are branched, you can see that if something is branched means what? The molecule is like either a ball or sphere, the molecule is more irregular. In that case, the molecule cannot pack as tight as when the molecule is branched. So that's when the molecule is unbranched. So if that's the case, the molecule will have what? Lower boiling point. That's the reason. Okay, that's the reason. Okay, so for example, these are 3 molecules. Out of 3, pentane, a quick one. 3 pentanes. Okay, 1, 2, 3, 4, 5. This is pentane. Another one is 2-methylbutane. Another one is 2,2-dimethylpropane. These are 3 C5H12s. Which one has the highest boiling point?
The first one.
Which one?
The first one.
The first one, the unbranched one. Okay, these 2 branched ones will be lower. This one, the boiling point is the lowest. Why? Because it's more what? Branched. Okay, they all have 5 carbons. Okay, all have 5 carbons. Okay, that's some quick concept check. Okay, now after we study physical properties, and after we're still studying physical properties, I want to show you guys more wonder. We learned so many hydrocarbons. Where are they coming from? Where are they? Did we make them, or where are they coming from? Okay, hydrocarbons are isolated from petroleum. Okay, they're petroleum. Petroleum is a mixture, but the main component of petroleum is what? Is a nasty mixture of hydrocarbons. Mostly alkanes. You watch the video, something there, petroleum is what? It's dark liquid, right? What is it? It's a mixture of all kinds of what? Alkanes, hydrocarbons. There are other hydrocarbons, but mostly are alkanes. Ranging from carbon number 1, which is natural gas, to carbon number 60. Whole mixture. Sometimes it's golden, sometimes it's greenish, darknish, depends on where the grades of oil. So the question is, how do we separate them? It's a mixture ranging from so many different carbons. How do we separate them? Based on their boiling point. Do you guys remember what's the trend of a boiling point? If you increase the number of carbons, the boiling point is going to what? Increase. This is exactly what a refinery does. You heat the oil. The one with more carbons will burn what? Slower. The one with less carbon will burn what? Faster to rise up. There's a tower called a distillation tower. So on the upper part of the tower, you separate what? With the one with what? Lower carbon. You can see that carbon 1 to 4, 5 to 12, 16 to... They're separated based on their what? Boiling point. Okay, that's exactly what oil industry does every day. Okay, based on the boiling, the lowest part is the heavy ones. Okay, the heavy ones. Good? Physical property? Okay, boiling point, melting point, and water solubility. Okay, you need to understand why and what's the logic behind those. Okay, be able to summarize by yourself and use them in real practices. Okay, and finally, chemistry. Okay, very simple for this chapter, chemistry. The biggest use of hydrocarbons, alkanes, in our daily life is to use them as what? Fuels. What is fuel? We burn them. Okay, combustion. Here are a few examples I showed you already. Natural gas, methane, you use that for what? For cooking. Propane you use in grill. Butane is the lighter gas, or sometimes you go to camping, those small can, the fuel can you buy for camping, that can is also butane can. Okay, and finally you drive. Gasoline is a mixture of octanes. Okay, your car is a bunch of C8 hydrocarbons, alkanes. You're driving them. So if you want to really study what the alkanes, and you want to prove it whether dissolving water, you can just get a glass of gasoline and try it and practice it. You just be careful, don't working with fire. Okay, so the only reaction we know about this chapter is what is reaction after we burn them? What do they become?
Yeah.
Okay, what gas?
Carbon dioxide and water.
Carbon dioxide and water. This is the general reaction for any hydrocarbon. If we supply enough oxygen, sufficient oxygen, we call the burning, we give it a name, combustion. And if we have sufficient oxygen, we call that combustion complete combustion. And this applies for any hydrocarbon. You can see that I put what? CHEM. It doesn't limit to alkane, it limits to anything as long as it's C and what? H. So what happens in a combustion is the molecule completely break down. Carbon bind with oxygen in the air to become what? Carbon dioxide. Hydrogen binds with oxygen in the air to become what? Water. Okay, that's the first thing you need to know. Okay, the final product for the complete combustion for hydrocarbons, including alkanes, always CO2 and H2O. The molecule is gone, totally bound, CH-CC bound or broken if we're in a combustion reaction. Next, you need to figure out from a certain hydrocarbon, how many molecules of CO2 and H2O can be produced respectively. The number of CO2 and number of H2O is determined by what? The number of C and number of H in your original molecule. If you have N carbon, then the number of CO2 will be what? N, because the C come from where? Hydrocarbon. The oxygen doesn't have any C there. So if you have 3C, that's 3. If you have 4C, that's what? That's 4, etc. Does it make sense, guys? The number of water is determined by what? By the number of hydrogen. Because water, each water has 2 hydrogens, so the number of water is half the amount of the hydrogen, m divided by 2. What does it mean? If you have 10 hydrogen, you end up with how many waters? 5 waters. Why? Because each water has what? 2 hydrogen. 5 times 2 is 10. Does it make sense, guys? Okay, here are 2 examples. See that? If C3H8 burned, you get 3 carbon dioxide and 4 water. Where's the 4 coming from? Half of the amount of hydrogen, the number of hydrogens. If you have C8H18, which is your gasoline, you end up with 8 carbon dioxide and what? And 9 water molecules. And you can also figure out the oxygen if you need it. Again, this is the general reaction for you. But most importantly, you need to understand what are the products and how many of them based on what? What hydrocarbon you're burning. Does it make sense, guys? Make sense? Tell me, complete combustion of this molecule will produce what and what, and how many molecules of each? Okay, take a look, give you 1 minute, work on your notes. Complete combustion of that molecule. We can draw that. And then tell me complete combustion of that will produce how many of what and how many of what? What were you doing? You're not doing wrong. I'm just asking,
Oh.
what were you doing?
Trying to find the hydrogens.
The number of hydrogens? Do you need to count? Or there's another way? That's why you don't need to count. That's why I'm asking. You don't have to count, right?
Right.
How many carbons? Take a think again. You may have counted wrong. All right. Okay, this is I like this question not because not only it tells you, ask you about the reaction, but also summarize a few things. First, like we said earlier, in a combustion reaction, what happens is what? The CC-CH bond or what? Broken. Is that right? You end up with what? CO2 and H2O. So that tells us at least one thing. Do I need to care about the structure? Do I need to care about the structure? Does the structure matter? Yes and no. If structure tells us C and H, but what really the structure is doesn't matter. I only need to know what?
Carbon.
How many C and what?
Hydrogen.
How many H? That's all I need. I don't care what the molecule look like in this reaction because combustion completely breaks everything. So if you look at the structure, how many carbons? 7?
9.
9 or 7?
9.
9. The chain is 7. There are 2 methyl groups. Okay, 9 carbons. And if it is a hydrocarbon, it is an alkane. If 9 carbons, how many hydrogens?
21.
20. 2 times 9 plus what? 2. You don't need to count. That's the safest one. Trust me. You count, you were lost count somewhere. So this is C9H20. Complete combustion will produce CO2 and H2O. The number of C is determined by what?
9 CO2.
The number of C in the formula, 9. So it will produce 9 CO2. The number of water is determined by what?
Half
The
of
hydrogen, which is what? Half of the amount of hydrogen, which is what? 10 hydrogen. So complete combustion of this little guy will produce 9 CO2 and 10 H2O molecules. Does it make sense? If I change the methyl here to here, it will produce the same thing, complete combustion. Why? Because in combustion, everything breaks down.
So if it were to come in exam, so we have to write if below we produce 9
9 molecules of CO2 and 10 molecules of H.
of the
H2O.
whole compound. Yeah.
Yes, that's the answer. 9 molecules of CO2 and 10 molecules of H2O. Does it make sense, guys? Good? Okay, again, like I said, I want you to get an idea about using this practice and also how the questions will be asked for each chapter. You understand the topic and apply that into a real exercise. Okay, and before we enter, a few words about the combustion. I know we talk about the main use of this fuel, of these hydrocarbons as fuel. We burn them. Okay, complete combustion is an ideal situation. rarely we can reach that level. So that means no matter how good your engine is, for example, in your car, your oxygen intake will never be sufficient. So that means there are a lot of incomplete combustion happening when you burn a fuel. No matter you're cooking, your stove, your barbecue, your car engine. So there will be other carbon oxides, such as carbon monoxide, or sometimes if your oxygen is really bad, you even get carbon black from combustion. That's why sometimes you go outside, you burn a wood, right? You see the bottom of your stove get black. That black is what? It's carbon. From what? From complete combustion. Incomplete combustion. And that's why our car, if you guys go down your car near the exhaust pipe, you will see a big box. Have you guys seen that? Near the exhaust pipe of your car, there should be a big box like that size, like a box shape. That's called a catalytic converter. That helps us to reduce the amount of CO from your engine to the atmosphere. Okay, every other car should have one. Somebody took it off. It should be illegal. Okay, but again, this reaction shows you ideal situation, but in real life, in reality, we always have incomplete combustions. So inevitably, if we burn fossil fuel, burn petroleum, we will end up with carbon monoxide. That's why carbon monoxide is one of the pollutants in the air. And also sometimes you will even see that some cars, if the gas is too fast, you see the right black thing out of the pipe. That's carbon mixed with other types of gases. Okay, water is always you always get water. Okay, so that's all for chapter 1. Okay, let me stop recording.